Now here's an application we haven't done before. It's nuclear fusion. This will be fun. So to bring a free proton toward a nucleus which has a positive charge and it's made up of protons and neutrons, right? So the nucleus has a positive charge. A repulsive force F of r is equal to kq q over r squared must be overcome, where q is equal to 1.6 times 10 to the negative 19, which is very tiny, coulombs is the charge of the proton. K equals 9 times 10 to the ninth nmc squared divided, or nm squared over c squared, sure. Newton meters squared over Coulomb squared. Q is the charge of the nucleus, and R is the distance between the center of the nucleus and the proton. Okay, so we're trying to bring a free proton, just one floating around, toward the nucleus. All right, so did you catch that it's a repulsive force? Because that will be important to us. So we just want to kind of make a note right there. It's a repulsive force. Okay, so find the work required to bring a free proton, assumed to be a point mass, from a very large distance away to the edge of a nucleus that has a charge of q equals 50q and a radius of 6 times 10 to the negative 11th meters. Okay, so did you catch that? Because that was interesting. It starts at a really far distance away, right? So we're starting at, and then we're talking about r. R is our variable here. So we have to actually make a note of that. So when you look at this right here, repulsive force, we'll talk about that in a second. So when you look at that, K, Q, and Q are all constants. R is the variable. R is the radius, if you will, if the free proton's circling around, right? So it's the distance between the center, see, center and the proton, right? So R is the variable. Okay. So we're going to start when R is really far away, i.e. infinity, right? That's where we're going to start. A very, very, very large distance away. And we're going to end right here. So that means that we're going to end at 6 times 10 to the negative 11th for R. Okay, now I need to figure out my function value. I actually don't need to figure it out right this second. I can wait on it and just substitute in at the values at the end, right? So we're not going to put in all of our values because look at the values they're giving us. K is right here, Q is right here, and then capital Q is 50 times that. Ick. So we don't have to substitute in right now. We can wait and hold off and deal with it at the very end. And that's what we're going to do, right? So we're going to hold off and we're just going to do everything in terms of letters. This is one of the reasons the physics teachers love that stuff, right? They love substituting. All right, so these are the radii that we're going to begin with. And I also want you to remember, because they want us to find the work. So work, remember, is the integral from a to b. In this case, it'll be of f of r dr, right? Because r is my variable. A little box around that because that's a formula. And we're going to hold off on substituting in because we can see these awful values. We're just like, nope, 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 nope. Right? So we will hold off on substituting K, substituting K, Q, and Q until the end. Because they're terrible. We don't want to deal with them. They're yucky. So we'll wait. Okay, so work is equal to, there's one other caveat to this. So work is equal to the integral of force. However, we have a little bit of a problem. They said they want us to start at infinity and they want us to end at 6 times 10 to the 11th, or negative 11, I should say, sorry. And then it's of our function, at least so it seems. So it's k, q, q over r squared, dr. So far, so good. You think you'd be doing great. However, it's a repulsive force, and we haven't dealt with that yet, but we have to. So because it's a repulsive force, matter of fact, let me highlight that. We have to fix that one of two ways. We either have to make K constant negative, right? So we either have to make this negative or we have to make the integral negative because it's repulsing, right? So the force is negative, right? Repulsive means that as r goes to infinity, the force goes to zero, and simultaneously as r goes to zero, force goes to infinity. So let me make a notes right here. So what does that mean? Repulsive means, it's just a physics thing, right? As r goes to infinity, force goes to zero. Or as r goes to zero, force goes to infinity, right? So to make that happen, K, either make K negative or the integral negative in order to keep the repulsiveness. And we're actually going to go with the integral because they gave us a positive K, so we're going to put it right here. We're actually going to put it right in there in order to make it so that it's a repulsive force. I have to do it in orange, sorry. It's a sneaky thing that they put in there for us, but nevertheless, we have to deal with it. So, all right. They gave us a positive case, so we'll make the integral negative instead. One way or another, we have to make it negative to make it repulsive, which is fine because K, Q, and Q are constants, so I can just pull them out. So K, Q, Q, come out here. One of the many reasons I can hold off on putting those suckers in. And then I'm going to reverse my limits of integration. And when I do so, the negative disappears. Nice, huh? Now the only thing that's left in here is r to the negative 2. Right? Because it's 1 over r squared, which is r to the negative 2. So I flipped it and made it go from small to large instead of from large to small. And I put a negative in front originally, and now when I reverse them, the negative drops away. That's one of the rules of integration that we learn in Calc 1. Okay, well, this is infinity, so I'm going to have to make that a limit. So this is the limit. Oh, I guess I can just put KQQ out in front. And then it's the limit as, I guess I'll call it b. b goes to infinity of the integral from 6 times 10 to the negative 11 to b of r to the negative 2 dr. All right, so that's equal to, again, KQQ, and then limit as b goes to infinity. And I can integrate this. The integral of that is r to the negative 1, right, which is negative 1 over r. Oh, sorry, r to the negative 1 times negative 1. So it's negative r to the negative 1. Let me just do it that way. I'm going to take that from 6 times 10 to the 11th. Or negative 11, I keep saying that, sorry, to b. All right, so again, KQQ, we will get to them eventually. We'll substitute them in. And then I'm taking the limit as b goes to infinity of negative 1 over b minus negative 1 over 6 times 10 to the 11th. Negative 11, sorry. Okay, so if I put infinity in, let's think about that. When you put infinity in, this will be negative 1 over infinity, which is a big fat 0. So it's going to go away. So that means that I have KQQ times 1 over 6 times 10 to the 11th. Negative 11. Sorry, it's very tiny. Right. So, this is the actual formula, right? Right there. So that's the actual formula. I just need to now substitute in my values. So I'm going to now substitute in K, Q, and Q. Right? I held off because I didn't want to deal with these numbers all the way through. And you'll see what I mean when I put them in. All right, so K is 9 times 10 to the ninth. Q is, little q, is 1.6 times 10 to the negative 19. This is fun. And then capital Q is 50 times another 1.6 times 10 to the negative 19, because it's 50 little q. Oy vey. And then they also want us to look at the units. So let's look at the units real quick. This one is in Newton meter squared over C squared, right? Coulomb squared. This one is in coulombs. This one is in coulombs. Oh, and I forgot the last piece of it. Oh my goodness. Losing my brain. For that 1 over 6 times 10 to the 11th. Negative 11. I'm going to say it right one time before this video is over, I swear. All right, so wonderful. This one is in meters. All right, so if you look at your units, coulombs cancels with coulombs and coulombs, right? And then, oh, sorry, this is 1 over meters. Sorry. It's 1 over meters because the meters is in the denominator, so I apologize. So that means that that meters there cancels with one of my meters here. I'll be left with Newton meters, which is joules, which is work. Hooray. So all I have to do is deal with all of these numbers. So let's look at what that looks like in Desmos, shall we? Because we're not going to do this by hand. So there they all are. 9 times 10 to the ninth, 1.6 times 10 to the negative 19th squared, because there's 2 of them, times 50 divided by 6 times 10 to the negative 11. There you have it. And so that's 1.92 times 10 to the negative 16. And that would be in Newton meters or joules. So we were just going to say that we found this with Desmos. We are not going to. 1.92 times 10 to the negative 16 Newton meters. There we go. And of course, if you want to say joules instead of Newton meters, that's perfectly acceptable.